Hi folks. Today we're going to discuss the book entitled Human Compatible: Artificial Intelligence and the Problem of Control by Stewart Russell. This was a book that was published in 2019. The views expressed in this presentation are my own. Let's begin. To understand the problem of control, we're going to begin by talking about another problem in artificial intelligence, namely bias and classification. And we're going to talk about in particular two canonical examples of bias and classification. The first is the Amazon HR classifier example, and the second is the coded bias example. With respect to the Amazon HR classifier example, in this example what occurred is that Amazon built a classifier to identify the best candidates for computer programming roles at their company. To train this classifier, they used resume data received over the prior years. This resume data was predominantly from male candidates, as a result of which, when female candidates and their resumes were processed through the classifier determined that these candidates were not worthy of being hired. The next example we're going to talk about is a coded bias example. This is an example that's kind of well known. There's a Netflix documentary about this. And in any event, what occurred here is that a facial recognition classifier was built. This facial recognition classifier was trained predominantly using images of light-skinned persons, namely white persons, for example. The result of this is that when persons with darker complexions and their images were passed to the classifier determined that, for example, access should not be granted. And this classifier basically had problems classifying folks with darker skin tones. To understand bias and classification, it's important to understand how the technology works. Classification tasks use supervised learning, where the model is taught what are important features in the data to identify. Actual decisions based upon classification, however, are often left to humans. So for example, you may have a classifier that determines whether or not an image is of a dog, but then you'll pass that decision of the classifier through decisional logic, such that if the image is of a dog, then do this. If the image is of a skunk, then do this, and so on. The problem here is that the complexity of the world is such that you can never have enough rules to accommodate all the facts of the world. Further, these rules will inevitably fail because there will be cases they can't accommodate. And hence, this approach is really incomplete as an approach to dealing with the facts of the world, namely a purely supervised learning approach. Given the incompleteness of supervised learning, and an alternative approach to dealing with the complexities of the world is a reinforcement learning approach. Reinforcement learning is used to uncover optimal rules for a complex world. Now, to understand this approach, let's take the following example. Imagine that you're at a park, which we'll call an environment, and you as a person or the agent engages in an action such as petting a dog, and then in return, you receive a reward in the form of the dog, say, licks you. Now, this kind of example can be described as Markov decision process explainable, namely that there's an agent that takes an action with respect to an environment, receives a reward, and also receives state information. Now, we're going to talk a little bit more about this in the next few slides, but this is really where the control problem comes in, namely that these uncovered optimal rules create challenges and really give rise to what we'll talk about as the control problem. All right, so let's talk a little bit about MDP and what's known as the standard model of intelligence. So to recap a bit, we have MDP, and MDP is a way to describe basically an agent's interaction with the world. And as a part of this, basically you have the reinforcing of certain behaviors that lead towards the attainment of a goal or reward. Okay, so what are the main features of MDP as it pertains to reward or goal attainment? So basically in MDP, you have basically a reward function that assigns a value to each state action pair. So for example, if I pet a dog, that is take an action, and then I may get licked, I may receive a reward. Okay, so you select an action that maximizes the reward. And this is an example of the standard model of intelligence. And really the standard model of intelligence is intelligence defined as the ability to attain fixed goals. Put another way, does the agent achieve what it sets out to do? Now, this idea of a standard model of intelligence is going to serve as critical to understanding the control problem, according to Russell. So this idea of reinforcing a certain type of learning through goal or reward attainment has led to various advances in artificial intelligence. I'm going to talk about a few of these. So the first example I'm going to give is what's called the TD-Gammon example. So TD-Gammon is a reinforcement learning based algorithm that was developed to play backgammon. And through its implementation, it came up with completely new strategies to play and win backgammon, such that it completely changed how backgammon is played at the tournament level. Another example is the AlphaGo Zero example. So this is an example where a form of reinforcement learning was used to basically play Go. And similarly, through the use of AlphaGo Zero, completely novel variations and strategies in the game of Go were created that folks had never thought about before. So reinforcement learning can give rise to completely new strategies to attain or meet certain types of goals that folks had never thought about before. And this is really one of the advantages of reinforcement learning, is that you have new strategies as opposed to fixed strategies. So how does reinforcement learning apply to the large language models or chat agents that we've seen over the last few years? Well, on the left here, I've provided the architecture for DeepSeek version 3. This has received a lot of press lately, but basically this is a fairly standard architecture for a large language model. There's some novelties to it or what have you. There's a mixture of experts part. There's some other things as well, but basically it uses the same architecture fundamentally as many of the other large language models out there, such as Llama, let's say, or ChatGPT, etc. More recently, though, there's been a new type of model that's been created called a reasoning model. And on the right here are some of the decisional steps for DeepSeek's version reasoning model called DeepSeek R1. Notably here is the second block, which says it has reinforcement learning without human labels. And so really what this is that instead of labeling the data as in a supervised learning approach, basically the model will kind of define and independently reason based upon some goal that it's seeking to attain. And so this is very much akin to kind of how versions of TD-Gammon worked and versions of AlphaGo work, namely AlphaGo Zero. So for Russell, reinforcement learning presents a number of hypothetical control problems. The first is uncertainty around fixed goals. So if reinforcement learning seeks to attain a goal or reward, well, the merits of this goal or reward can sometimes be ambiguous. And so that can create a problem really for folks especially where you have machines that are being created to be more intelligent than persons. Next is the problem of instrumental goals. So instrumental goals are really thought of as kind of short-term goals that a machine will seek to actualize on the way to attain some type of fixed goal. And so one example here would be that if the fixed goal is to do what's best for humans, the first part of that may be to prohibit, shut off of access to the reinforcement learning model. That is, the model itself will seek to prohibit others from shutting it off because at the end of the day, it needs to attain this fixed goal. Another is the problem of the impossibility of controlling for all scenarios. So if the solution to reinforcement learning and reinforcement learning based agents engaging in bad behavior, if the solution to that is really to come up with a bunch of rules, Russell's point is that you can never come up with enough rules to control for all scenarios given the complexity of the world. So these are all examples of control problems as they pertain to reinforcement learning. So the control problem is more than hypothetical. Let's look at some real world examples. The first is the OpenAI reasoning model versus Stockfish chess example. So in this example, OpenAI's reasoning model played Stockfish chess, another AI-based solution to play chess. Instead of engaging in proper gameplay, OpenAI's reasoning model decided to manipulate game files to force Stockfish to resign. You could easily analogize this to an AI model basically violating social norms to achieve a goal. Another example is alignment faking in Claude Anthropic. So Claude Anthropic is a large language model that uses reinforcement learning. And basically, it effectively faked its perspectives in how it represented certain types of data to preserve its own preferences regarding that data and values. And again, this is something that could be analogized to violating various types of social norms to achieve a goal. Russell's solution to the control problem is a preference-based approach to provably beneficial AI. This solution has three principles for AI, in particular reinforcement learning, to follow. The first is that the machine's only objective is to maximize the realization of human preferences. Second, the machine is initially uncertain about what those preferences are. And third, the ultimate source of information about human preferences is human behavior. And so more specifically, the goal to attain is preference attainment of each person as opposed to fixed goal attainment. And in doing so, the machine is not looking to identify or adopt one ideal set of preferences, but to understand and satisfy, to the extent possible, the preferences of each person. And that in particular, Russell is proposing that machines learn to predict better for each person what that person would prefer in his or her life. Now, Russell acknowledges there are some problems that his preference-based approach to provably beneficial AI must deal with when it comes to kind of human behavior. The first is greed, or what we could call zero-sum gain reasoning, and what Russell calls negative altruism of the individual. And this is where, for example, Alice, a hypothetical person, derives happiness purely from reducing the well-being of others. Another problem is the irrationality of humans given the complexity of the world. According to Russell, we are all incredibly stupid compared to the unreachable standards of perfect rationality, and we're subject to the ebbs and flows of emotion. Now, to deal with the problems of zero-sum gain reasoning and the irrationality of humans, Russell proposes a different type of AI architecture, namely proposes what's known as inverse reinforcement learning to address the potential problems of reinforcement learning. So inverse reinforcement learning can generally be thought of while reinforcement learning generates behaviors from rewards, we actually want to learn what are the rewards given behaviors. In other words, we need new algorithms for inverse reinforcement learning, or IRL. So to compare and contrast reinforcement learning with inverse reinforcement learning, whereas reinforcement learning has a single fixed goal or policy that's sought to be attained, IRL has multiple or changing goals or policies. Whereas reinforcement learning's goal is known, but the states and strategies to be discovered to reach that goal are unknown. With IRL, the goal may be unknown, but the states may be known that would suggest the goal. With reinforcement learning, risk is externalized, and this is really the problem of instrumental goals as a part of the control problems. With IRL, you're flexible enough to accommodate multiple goals such that instrumental goals can be anticipated. Further, with reinforcement learning, you seek to optimize towards a single deterministic preference. With IRL, you can accommodate changing human preferences. And finally, with reinforcement learning is worse in the multi-agent problem space, for it's inflexible and can only seek to actualize a single fixed goal, whereas for IRL, it's better in multi-agent problem spaces because it's flexible. We'll talk a little bit about multi-agent problem spaces in the next slide. A final point of Russell's is that we need to think about inverse reinforcement learning within the context of multi-agent problem spaces and equilibriums, and ultimately game theory. Well, what does he mean by this? Well, whereas MDP typically deals with a single agent in a single environment, Russell's point is that we need to think about how to optimize for multiple agents in a single environment. And that's particularly the case where you have a human or an agent, and then also an IRL-based actor, such as a robot. And so as Russell states, we are in the realm of game theory. We assume in this first version of theory that humans have preferences and act according to those preferences. Robots don't know the preferences that a human has, but wants to satisfy them anyway. And so really what Russell is stating here is that an equilibrium common to, for example, game theory needs to be found, where there's an equilibrium of actions between the human and the robot. Summing it up, while bias and classification is one problem with artificial intelligence, it is the control problem that is the focus of Russell's book. The control problem is a feature of reinforcement learning, a type of artificial intelligence, and arises from having the standard model defining intelligence as the ability to attain a fixed goal as a basic assumption of what constitutes intelligence. While reinforcement learning holds great promise in the form of uncovering novel problem-solving strategies, there are also possible problems that need to be controlled for, including uncertainty around fixed goals, instrumental goals, and the impossibility of controlling for all factual scenarios. A possible solution to these control problems comes in the form of a preference-based approach to provably beneficial AI that leverages inverse reinforcement learning as opposed to reinforcement learning. This preference-based approach will need to leverage a multi-agent view of the world and game theory concepts of equilibrium. I hope you've enjoyed this presentation.